Hi everybody, welcome to our video about rates of change. This is our third video in our applications of derivatives section. In this video we're going to see a wide range of examples of using rates of change to solve problems. Initially we're going to look at an example involving the motion of an object. Then we're going to look at an example involving the change in a variable with respect to time, where the variable is not related to motion. And then we're going to look at an example involving the change in a variable with respect to some other variable that's not time. So let's begin. We can use calculus to find the rate of change of a function, as we've seen in our previous videos. So what we do is we find the derivative of the function to get its rate of change at a point. So this can be used in a number of different contexts. So for our initial example, we're going to look at the motion of an object. Here we've got a plot of distance traveled versus time. So looking at our chart here, on our x-axis we've got time in seconds, and on our y-axis we've got a distance in meters. And we've got our function highlighted in blue giving us our distance of our object for a given value of time. So if we look a little bit closer, at time 0 seconds, our object is at a distance of 0 meters, so it's at our start point. At a time of 1 second, the distance of the object has increased. At a time of 2 seconds, it's increased to a further amount. From 2 to 4 seconds, the change in distance with respect to time appears to be relatively constant, shown by that straight line. And then at time 6 seconds, our object appears to have come to a halt. So our distance is no longer appears to be changing. So we can investigate this further by using calculus. And the first step in doing this is to express the behavior of the object using a mathematical function, because then we can start applying calculus to the function to determine further information. So we want a function to describe the motion of the object. This can be found. The distance traveled is a function of time. So we're going to represent distance s as a function of t. The movement can be described using a piecewise function. So this will involve more than one sub-functions to describe the motion at different times. So for a time between 0 and 2 seconds, the distance is described by the sub-function t squared. For a time between 2 and 4 seconds, the distance is described by the sub-function 4t minus 4. And for a time between 4 and 6 seconds, the distance is described by that third final sub-function. So now we've got a piecewise function that expresses the distance as a function of time. So now at this point we can now apply calculus to our function to determine more information. So we're going to look here at the relationship between distance and velocity. The derivative of the distance s with respect to time t, ds dt, that's the rate of change of distance with respect to time. Well, the change in distance for the change in time, that's the velocity of the object. So if we find the rate of change of our piecewise function with respect to time, that piecewise function that describes distance, we can actually determine a function which describes the velocity of the object as a function of time. So what we want to do here is we want to take the derivative of of our piecewise function with respect to t. So previously we had our piecewise function, distance s as a function of t, was those first three sub-functions on the left-hand side of our screen. Well, just below them, we've got our velocity as a function of time. So that's the derivative ds dt, the derivative of s with respect to t. So looking at our first sub-function, t squared, the derivative of t squared with respect to t, using our power rule, that derivative is 2t. Our second sub-function, 4t minus 4, its derivative with respect to t is 4. And for our third sub-function, its derivative with respect to t, that works out to be 12 minus 2t. So now, using calculus and finding the derivative, we've determined the velocity of our object as a function of time. And we can plot these functions in our chart here on the right hand side. So we've essentially, by finding the rate of change using the derivative, we've generated a whole new data set of useful information about our object, which we can see here. We've got time on the x-axis and we've got velocity on the y-axis. So now we can see that at time 0 seconds, the velocity of our object was 0, it was stationary. At 1 second, the velocity of our object was 2 meters per second, so it had steadily increased. From 2 to 4 seconds, our velocity of our object was at a constant 4 meters per second. And from 4 to 6 seconds, it appears that our velocity was reducing, with a velocity of 2 meters per second at 5 seconds and a velocity of 0 meters per second at 6 seconds. So it appears that our object had come to a halt at 6 seconds with a velocity of 0 meters per second. But we can go further than that. We can also look at the relationship between velocity and acceleration. The derivative of the velocity with respect to time, dv dt, is the rate of change of velocity with respect to time. And the change in velocity put a change in time, well, that's the acceleration of the object. So our acceleration a, as a function of t, that's equal to the derivative dv dt. So if we look at the bottom left-hand side of our screen, here we've got our function from the previous slide. Our velocity as a function of time was ds dt, the derivative of distance s with respect to t. And we'd seen earlier, that's equal to the three sub-functions here. What we now want to do is we want to generate a new data set of the acceleration of the object with respect to time. And we can do that by using calculus and finding the derivative to determine the rates of change of the object for those different time periods. And here we can do that. So at the bottom left of our screen, we've got a new piecewise function describing the acceleration a as a function of t. That's equal to dv dt, the derivative of v, the velocity, with respect to t, which itself is the second derivative of distance with respect to time, written as d squared s all over dt squared. And when we calculate those derivatives, our first sub-function for velocity was 2t, the derivative of 2t with respect to t, that's 2. Our second function for velocity was 4, and the derivative of 4 with respect to t is 0. And our third sub-function for velocity was 12 minus 2t, and its derivative with respect to t is minus 2. So now we've got a new piecewise function describing the acceleration of our object with respect to time. And we've plotted that on the right hand side of our screen here. So now we've got a brand new data set of information describing more useful info about our object, specifically the acceleration for any given time between 0 and 6 seconds. So here we can see we've got time plotted on the x-axis, acceleration plotted on the y-axis, and we can see that between 0 and 2 seconds we had a constant acceleration of 2 meters per second squared. So our velocity was continuously increasing. Then we can see that between 2 and 4 seconds we had a constant acceleration of 0 meters per second squared. So there was no acceleration and we had a constant velocity. And we can see for a time of between 4 and 6 seconds we can see that our object was decelerating. So there was a constant acceleration of minus 2 meters per second squared. So what we've just done is we've just started with a plot of distance with respect to time. Then what we did was we generated a piecewise function to describe the behavior of the object. So we had a mathematical function that described the distance of the object with respect to time. With that mathematical function, that allowed us to then start using calculus to determine further information about the behavior of the object. So we were able to determine its rate of change of distance with respect to time, which gave us the velocity by taking the derivative. And then we found a second derivative to give us the acceleration. So we got from distance versus time to velocity versus time by taking that first derivative. And then when we took our second derivative, that brought us to acceleration versus time. So that was an example specifically involving the motion of an object. But it's important to remember that we're not limited just to examples involving motion. So using calculus to calculate velocity and acceleration from distance and time data, it's a common learning example, but we can do lots of other things as well. So we can use calculus to find the rate of change of other variables than those related to the motion of objects. And we're going to see another example now. Next example is one of cell growth rate over time. So not involving the motion of an object, but involving the concept of growth. So here's our example. Say we were in a science laboratory and we've got a population of cells that's growing in a petri dish. The size of the population at a given time, it's given by the following equation. So the population, represented by a variable p, that's equal to 5t squared minus 8t plus 10, where t is the time in hours, and the equation is valid for a t ranging between 0 and 10 hours. So we've got a mathematical function that describes the population of cells in the petri dish as a function of time. Well, with this mathematical function, we can use this as a starting point to apply calculus, and we can learn more about the situation. So the rate of change of the population at a given time is given by the derivative. So the derivative of our function with respect to t, dp dt, is equal to 10t minus 8. Because looking at our first function, the derivative of 5t squared, using our power rule, that's 10t. The derivative of minus 8t, that's equal to minus 8. And the derivative of plus 10, remembering our constant rule, that's equal to 0. So our derivative works out to be 10t minus 8. So with our derivative, we've got a new function that's describing the rate of change of the population at any given time between 0 and 10 hours. We just have to substitute in our value of t. So, for example, at a time t equals 6 hours, the population is growing at a rate of 10 times 6 minus 8, which is equal to 52 cells per hour. But we could also look into, well, how much is it growing at, say, 1 hour? We simply substitute in t is equal to 1. So we get 10 multiplied by 1 is equal to 10 minus 8, which is equal to 2. So there's a very big difference in the growth rate of the population. At 1 hour, it's changing by 2 cells per hour, but at 6 hours, it's changing by 52 cells per hour in the petri dish. So that's an example of rates of change involving growth rather than the motion of an object. And there's plenty of other contexts that this can be applied in as well. Calculus is used in a wide range of different fields: science, engineering, economics, medicine. I mean, you could apply it to financial quantities. There's a whole different range of variables that can be investigated. So, something to highlight as well is that in our previous examples, we were looking at the change in a variable with respect to time. But we're not limited to just looking at cases where we're looking at changes of a variable with respect to time. So we can also examine the rate of change with respect to some other variable that's not time at all. So to do this, we differentiate with respect to that other variable, as we're going to see in the next example. So in this example, we're going to talk about marginal cost. Marginal cost, it's a term from economics, where a function f of x describes the cost of production of x number of units. The marginal cost of production, df dx, describes the rate of change of cost with respect to the level of production, so the number of units produced. And we can use the marginal cost to approximate the cost of producing one additional unit. So, to go further into this example, the cost to produce x units of product is given by this equation. C as a function of x is equal to x cubed minus 6x squared plus 10x. So our question is, if 12 units are being produced, how much extra would it cost to produce one more unit? Well, the marginal cost of production gives approximately the cost to produce one more unit, and the marginal cost of production is equal to the derivative of the cost of production function with respect to the number of units produced. So what we're looking to do is to calculate the derivative dc with respect to dx, dc dx. That's equal to, from our function c of x is equal to x cubed minus 6x squared plus 10x, our derivative dc dx is equal to 3x squared minus 12x plus 10 when we apply our differentiation rules. So now we have an expression for the marginal cost of production for a given value of x. So we were producing 12 units, so our value of x is 12. So now we can work out the marginal cost of production, approximately the cost to produce one more unit when we're already producing 12 units. We can work that out by substituting in 12 into our equation. So for x is equal to 12 on our last line here, dc dx is equal to 3 times 12 squared minus 12 times 12 plus 10, which is equal to 298 euro. So we've worked out that it would cost approximately €298 extra to produce one more unit under these circumstances. So this has been an example from economics of a rate of change that doesn't involve the change in a variable with respect to time. It's in fact two other variables. So to summarize, calculus is the mathematics of change. And as we've seen, we can use differentiation to determine rates of change of different variables in a number of different contexts. We can use this information to solve problems. So thank you for watching this video. Please proceed to the next video to see more applications of derivatives. Thank you for your time.